Welcome back to my channel. Today we're going to go into further studies mathematics, and we're going to go into how we sketch piecewise function graphs. Piecewise function graphs. What's a piecewise function graph? It follows the same way. It's just that there are restrictions placed on every graph, just like we have on other graphs, just like we have an absolute value bar graphs. So those restrictions must be respected for you to have your graph. Those restrictions must be respected. Let's go into the question. We'll do more of the explanation as we try sketching the graph. The question is asking us to sketch the graph of g of s. This is the graph. It has many pieces all in one. Many pieces all in one, hence the name piecewise. But these pieces can only be sketched if we obey the restriction placed on that particular function. So for this graph, we have x plus 3 as the first graph. And the first graph being x plus 3, it means that it's a linear graph. Y equals to x plus 3. The y-intercept there is 3. Because y is always c. Remember, the format is mx plus c. So to get our x-intercept, we make y 0. So our x-intercept will be -3 and 0. So we have these 2 points. So let's pick our points 5, 2, 4, and 6 as y here, -2, -4, -6. I'll use the same scale for both x and y axes. Now let's look at this. Let's sketch this. I have 0 and 3 as my y-intercept. X-intercept is -3 and 0. Now, what is the restriction? The restriction says that for this particular graph, x is greater than -5, but less than -3. That means every other place, it must be within this range. So it must be between -3 going up to -5. So I can only sketch this part of the graph. So remember, it is greater than -5. That means it will go all down, but it is less than -3. Hence the open dot here. So this is the graph. Every other part cannot be sketched because we have a restriction. Let's look at the other one. We have the second one. Y is equals to 3. 3, y is equals to 3 will give us a horizontal graph at 3. But if it is a horizontal graph, it runs from 3 all through. But we have a restriction again. It is less than -3, so the horizontal graph from 3 can only start when x is also from -3, and it says greater than -5, so it can also go only this way from the -3. Now let's look at the next one. This one says y is equals to -2. It is also a horizontal graph. A horizontal graph at -2, but they say x must be less than -5. So it's also a horizontal graph, but x must be less than -5. If this is our -5, it means this graph should start here, somewhere here. X must be less than -5. X must be less than -5. So it can only go this way. Less than -5. So we have a horizontal graph going this way. Please, on a proper grid line, you will see the differences. Maybe this graph will not be touching. And then let's go to the last one. The last graph here, we have y is equals to x squared plus 1, which is a parabolic function. Plus 1 means the turning point, and the y-intercept is at the same place if we don't have a p. It's at 1. So we have a parabolic graph. But here, the next thing we need to check is our y-intercept. If we make x 0, we will not have any y-intercept. because we will have 0 equals to x squared plus 1. X squared will give us negative 1. Root of negative 1 will give us an undefined value. So no y-intercept. But we focus on the restriction. X must be a value greater than negative 1. So from negative 1, we have our graph. It must be greater than negative 1. So we can only represent this arm from negative 1. Remember, this is negative 3 and this is at negative 5. So we can only represent this arm. Because x is greater than negative 1, so it must be from negative 1 to the positives. So this is a piecewise function graph for this given function. Remember, what makes it pieces is obeying the restriction. So it's slightly different from what we do in absolute value graphs. Here we have multiple restrictions, multiple graphs in one function. And that is the pieces that we have arranged. So this is a piecewise graph for that function. Let's answer the following questions. Now, the first question, they are asking us to get g of negative 2. This is g of x, so of negative 2. We only focus on where this condition is made. Of all these graphs, when will x be negative 2 and be valid? So here, there's no negative 2, here it doesn't work. Here, there's nothing, it doesn't work. Here, there's nothing. So g of negative 2, in this case, what can we say? G of negative 2, what can we say? It's less than negative 3, greater than negative 5. Okay, let's write this. Greater than negative 5, less than negative 2. For the first one, greater than negative 5, less than negative 2, so let's go to negative 5. Greater than negative 5, that less than negative 3. That is the graph. Greater than negative 5, less than negative 3. For this, greater than negative 5, less than negative 3. So this is 6. And the next one, less than negative 5, this is 6. So we have this graph. When will it be x? When will x be negative 2? It doesn't touch any of the graphs. So this does not apply. As simple as that. It does not apply because all the pieces of the graph has not been affected by anything. So it doesn't apply at all. So that does not exist. And let's go to the second one. G of negative 4. On these graphs, when will x be negative 4? Let's look at this. X is negative 4 here. X is negative 4 here. It's touched two graphs. The first one, if this is negative 4, for the first one, we will have that y is equals to 3, because that is the horizontal graph for 3. And then let's go to the second one. The second one is the linear function x plus 3. So that will only happen here and here for x to be negative 4. So for here we have y equals to 3. For the second one, this is the function, it's a linear function. So g of negative 4 applies to the linear function, so we have negative 4 plus 3. So g of negative 4 for the linear function will be negative 1. And let's look at the last one. We want g of 2. We check the value of x on the graph where it touched 2. Only the graph that touched 2 will satisfy this condition. So we go into this. It is only this one that will touch 2. So the graph in question is only the parabolic function. So g of 2 applies only to the parabolic function. So we will have 2 all squared plus 1, and g of 2 will give us 5. So whatever they give us, please remember the approach is to check that value of x where it touched the graph, the particular piecewise function that it touched. And be very particular about your restrictions. And be very careful, just like what I did previously, I was taking this as less than -5, whereas it's greater than -5. So it's greater than -5 and less than -3, greater than -5, less than -3, and this is what we have. Now, when we have two graphs being joined together to each other here, this is what we're going to treat in the next section. We say that there is discontinuity in the graph. This one stopped here and the other one continued. When we have such cases, we say we have removable discontinuity. For removable discontinuity, it means the limit of f of x is equals to the f of x at that point. When there's nothing linking them, it means we have a jump discontinuity. And that means that the limit for that function does not exist. But that is a topic for the next video. So if you have any question on this, ask, and we'll give you more clarity. Keep sharing my video. I'll see you in the next video.